All right, welcome back to part two of a Canary overview. If you remember in the first part, hopefully you've seen that, we did a really 30,000 foot view of the Canary system, the problems that Canary works to solve, and some of the fundamental, if you will, framework, the three pillars: openness, security, and adaptability that our system is built upon, as well as we talked about the 7 main applications that work together to create the Canary system. The goal today for this video is to dive deeper into part 1 of the Canary system, and that is the collection and storage of your process data. So we're going to highlight the data collectors, the store and forward, and the Canary historian to do that. Let's talk about data collection. So we have a series of drivers that we've developed to help you collect data from your devices and your systems and other databases. The most important thing I want to note is that all of our data collection is unlicensed. We do not make you consume any type of license or pay us for any of these drivers. So our OPC, DA, and UA collection points are probably our most commonly used, as well as our Sparkplug and MQTT JSON varieties for MQTT subscribing clients. Additionally, we have multiple SQL databases that we can connect to. Those include MySQL, SQL Server, various PLCs and SCADA devices. So on the PLC side, we support connectivity directly to your Siemens S7, your Allen Bradley Compact Logics, as well as to Modbus PLCs. This is a nice piece because if you have some data at the edge and it has value, but it doesn't necessarily maybe have extreme value, you might be hesitant to going out and buying an OPC driver just for a couple of tags. Well, by being able to go directly to PLC, you'll be able to reliably capture that data and bring it into the Canary system. Additionally, we've been working on connectivity with actual physical hardware at the edge, things like Opto22 devices, E1 products by HMS, another example. We've also continually been upgrading our SCADA connectivity, so native collectors and native interfaces for things like Ignition by Inductive Automation, TATSoft, Signet for all of you oil and gas midstream or upstream users, as well as a manual data entry component. As the thunderstorm here in Northwest Arkansas rolls in. Timing is everything. I'm not sure if you're picking up the thunder on the microphone or not. But we have a manual data entry component as well, so that if you have part of your process, folks that are still maybe recording things on a clipboard and into Shift need to bring in that data, or perhaps they're keying it into CSV files, we can both give them a way to add that manually, or we can automatically ingest CSV files that get dropped into a directory. All of our drivers connect and process this data to get it ready for the Canary API. The Canary API is how we load this data into the rest of our system. We've chosen to make that API public and, again, unlicensed. So that means if there's a driver that you would like to integrate, if there's a collection device that maybe you have a piece of hardware and you'd like to tie in your hardware into the Canary system, both our .NET and our web API, they're made publicly available for you to do that. Now, once the driver's been configured, now it's time to move that data to the historian. And to do that, we use store and forward technologies. This is important because we understand that many of you are going to operate in areas where the network isn't a piece of cable that's plugged in from one device to your server. You might be going across cellular, you might be going across line of sight communication methods, but we know that data integrity matters. And so we wanted to build in some real nice redundancy and ways to make sure that anything that you are collecting on the driver side will arrive in the historian. So our store and forward has the capability by default that if at any point it loses awareness of the historian, it will automatically buffer that data locally and write it to local disk on device. When that happens, your admin team can be notified that data has stopped flowing into the historian. Most importantly, when the network recovers, or perhaps the historian server that was maybe taken offline for some routine patching, when it is back available, all of the data that was buffering and all of the data that was written to local disk back at the device or at the edge side automatically backfills and will come right back into the historian. Additionally, we allow a single data logger or one of these drivers to target multiple historians. And each one of those historians that it targets, think of it as maybe a primary or redundant site historian, or it could be a historian that's local as well as one in the cloud or at corporate. Each of those historians gets their own independent data stream. So even if one of the networks is down, the other historian is still receiving data. Or if one of the servers is offline, the other server is still receiving its own independent data stream. Also to mention, for the larger complex corporate environments, for level 3.5 DMZs, we support a proxy server as well. So if you remember from the very first conversation in the first video, we talked a lot about openness, we talked about secure, and we talked about adaptability. And so let's review how we meet these marks, how we hit our own internal check boxes using our data collection tools. How's it open? Well, not only are we making our .NET and our web APIs publicly available, we're also standardizing on consistent protocols that are industry adopted everywhere. So high adoption rate like OPC and MQTT means that by supporting those protocols, we're making sure that we stay open and interoperable for as many solutions as we can. How's it secure? Well, all of those data feeds, when the driver is configured and we're creating that data stream to the historian, all of that is using TLS. So that means that we can both authenticate and authorize not just our users when they consume data later on, but also our actual loggers themselves. So no data can arrive into the historian when security has been enabled that you don't know the client that's publishing it to the historian, that it's not authenticated and authorized. How's it adaptable? Well, because we've chosen not to license any of these technologies, that means that you can choose to deploy our collectors where you see fit and when you see fit without thinking about licensing cost as being the limiting factor for you. All right, so that would cover the data collectors in the store and forward. Now, if everything's going correctly and you've got your data sources configured and your store and forwards in place, then we should have data arriving at the Canary historian. The historian is really the piece of technology that we are most well known for at Canary. That's because it's a NoSQL proprietary specific time series written database. So the only thing that Canary focuses on with our database technology is time series data. We have become extremely well versed at how to store time series data. It's what we geek out on, if you will. And most important to our database is this concept of lossless compression. So think about it this way. If you are able to sample every data stream and all of the data that was flowing through that data stream and compare it to the data as it shows in the historian archive, it will look the exact same. It'll look the exact same the day that you log it to the archive. It'll look the exact same 7 years later if you look at the historian. So we do not use any type of compression algorithms that trim, interpolate, average, or drop any of the values as they are written from the loggers. That means for you, when you later on want to read data out of the historian, you can have complete confidence that whatever's in the historian is exactly what was being processed at the edge. The key to all of this is that we are able to achieve a 3x compression rate, even keeping all of the values. A single server can scale to more than 2 million tags. So a single historian instance can handle more than 2 million tags. And our performance is consistent. It's consistent no matter how long the historian is being used. It's consistent no matter how many tags are being added or written to the historian. It's consistent no matter how much data is being retrieved from the historian. We can update or write at 1.5 million new TVQs, timestamp, value, quality, so per tag, per second. So that's 1.5 million tags updating at one update per second, or it's 100,000 tags updating 10 times a second. But 1.5 million updates per second, value changes per second for the write speed, and the read speed almost double that at a little bit more than 2.5 million reads per second. We've optimized for reads because we understand that even though you'll write data consistently, you can read data in much larger batches, if you will, or you might read the same tag multiple times, where you might only write to that tag a few times a day. Because of our performance, if you think about it from this philosophy, because our performance has always been so high on the write and the read, and because our performance doesn't degrade over time, Canary has never needed to devise a compression algorithm that removes data, interpolates data, trims data, averages data for its long-term storage. Because there's not a performance issue, we don't have to try to solve how to keep the system performing. That's the beauty of the proprietary database that we've created. And the Canary Historian has been in creation and development since the mid-'80s. We're currently on the 22nd, here in it is May 2022. We're on the 22nd iteration of our product, version 22. And important to note is we continue to work on the underlying technology of our historian. So even though we've been developing it since the 80s, it's not technology left over from the 80s. Perfect example of that is on our data collection side, we've completely moved away from WCF and are now embracing gRPC as our underlying technology. And this is a differentiator between Canary and a lot of the competition in the market. We really work hard to do complete overhauls on our product and make sure that continually we're taking advantage of the greatest technology that's available to us, proven, hardened technologies. What's unique, though, is that our upgrade path, we don't lose the ability to upgrade from older product to newer product. So I'll just share a story. It was, I guess now, it was pre-COVID, so it was about 3 or 4 years ago. We had a user contact us from the Netherlands. They were running a Canary version that they had not updated since 1994. So that would have put them on, I believe, version 5 or 6 of the product. They wanted to go to version 19, which would have been current release at that time. We were able, through just 2 upgrades, so going from, I think it was going to version 11, and then installing over top and upgrading from version 11 to version 19, we were able to not just take the archive over the course of an hour or two and update it to current version, but we were also able to take all of their trend charts. Even though their old trend technology was built on ActiveX, they didn't lose a single trend chart. They didn't have to rework any of the trend charts. They came right into our HTML-based trender through another upgrade utility. So backwards compatibility is extremely important to the DNA of our product. Let's talk a little bit about how the actual historian works. At the highest level, we give you the ability to organize groups of tags into data sets. So just think of a data set as a folder. And so when you're logging data from the device or from the edge and pointing it towards a Canary historian, you make a decision at the point of logging configuration under what data set do I want my group of tags to live. It is the highest level of organization inside of the historian. Now, once a tag lives in a data set, it'll stay in that data set for its life. So the data set name for that tag, we actually pre-pinned to the path of the tag. So if I have two data sets, one west, one east, it's maybe just how I've named them, my tag path is no longer tag 001. It's now west dot tag 001. The dot inside of a Canary tag name represents a parent-child relationship, or it represents structure within the tag itself. We don't place any type of fixed limits on the number of data sets that you can create. And so essentially you're creating multiple databases inside of your historian. Now, when we look inside of the actual data sets themselves, we will find that within the data sets, we have a collection of historic database files, or HDB files. So within each data set, think west and east again, we will have multiple HDB files. Only one of those files is actively being written to or in the open, currently open. We run a new HDB file for each day that you are logging data. So at midnight, today's current active and open HDB file will be closed. That means that if I've been writing data for 30 days to my data set, I will have 30 HDB files. This becomes extremely useful and convenient for running basic backup or disaster recovery processes, because each of these HDB files, the name of the file contains both the data set it's in as well as the day that the file was being written to. If at any point there's any type of alert or issue with any of these HDB files, your system admins get automatically notified, and Canary has a lot of processes built into our solution that are automatically managing these HDB files for you. So an HDB file runs through a process. When it's closed, if that validation process fails, the file's taken offline, the admins are notified, a process is recommended to the admin to recover that file, and Canary basically just runs that process with the admin's approval and does any type of repair as necessary to that file. So let's talk about what's actually inside of that file. Within the file itself, we have our complete tag list. So every single tag that's being written to that data set for that day is listed inside of that HDB file. Beyond the tag list is also the list, of course, of all of the timestamps, all of the values, and all of the qualities. Any type of metadata, properties for those tags, things like engineering units and descriptions, set points, any type of custom metadata properties that you'd like to write. You're not limited to what type of metadata you can log. You can create as many custom fields as the protocol of your logging supports. So for instance, OPC DA only supports a handful of metadata fields, where OPC UA or MQTT support custom fields of your liking. Everything is contained inside of this one file. So there's no external reference tables that I need in order to unpack and unlock and use the data that's inside of one of these files. So again, for disaster recovery, if I have a thumb drive that I need to put 30 days of HDB files on and hand that off to have it plugged into another Canary system, I only need those 30 HDB files, and I only need a Canary system that allows for licensing for me to plug that in and bring those files in. If we talk a little bit about overall specs, what we typically recommend for more of a site-specific historian versus an enterprise-specific historian, the technology is the exact same. So it's not a different install for a site-based historian versus an enterprise historian. We just know that the general needs of those two applications are different. The workload is typically different. And so, so is things like usually tag count, number of queries. And so at a very high level, without getting into too much detail about your needs, we typically would start off by saying we'd recommend for a site historian quad core, 8 gigs of RAM. Everything needs to run .NET 4.5 or newer. And on the historian for an enterprise, we'd always say recommend starting at no less than 6 cores and 32 gigs of memory. Of course, we run on virtual machines as well as physical machines. That means you can put Canary in Azure or AWS. Right now, we're continuing to explore and work through how we can also run Canary in Linux-based or containerized environments. All right, so we've talked a lot about the historian. Let's bring it back to our open, secure, and adaptable, or OSA, as you'll hear me refer to it. How do we take a proprietary historian, a database technology that's ours, and make it open? Well, this is where we have to really think of the best of both worlds. So there are things about proprietary technology that give you better performance. What's important to us, though, is that we don't cause complete platform lock just so you can take advantage of that technology. So we start by making it easy to move files between Canary servers. So if a Canary server is licensed to have 1,000 tags, and you've got 500 tags over here in this HDB file, and you want to move it over to another historian, as long as the licensing is available for those extra 500 tags on the second historian, not a problem. There's nothing that would keep you from other, of course, than your physical security best practices, right? Accessing the archive itself or the machine itself. There's nothing that would stop you from our side of taking those HDB files and moving them to another server. At the same point, because our APIs, and you'll find in other videos here to come, that you can read data from those Canary archives, again, using open APIs, even though it's in proprietary format, even though it's a binary file that's encrypted and completely protected, you still can pull the data out of it using standard protocols and therefore format it as you would like and put it into another database down the road if that's what your plan is to do. Secure, I've already mentioned it's encrypted on rest, just like it was encrypted in transit, it's encrypted at rest, and it's secure from loss of integrity of the data because we are using a lossless compression algorithm, and also we are validating every one of those HDB files when we close that file. And adaptable. Single server can scale to more than 2 million tags, which is about 1 million tags more than most organizations will even dream of trying to capture in a historian currently. But let's say that you're a huge organization and you know 2 million tags is just not going to be enough on a server. We give you the ability to cluster our servers so that if you needed 8 million tags, we'd be looking at 4 Canary servers standing in parallel. But what's important is that from the publishing of that data or from the client querying that data, they would not have to see 4 records. They would see 1 volume, even though it is 4 independent archives. All right, well, I hope this has been helpful for understanding part 1 of our 3-step process, collecting and storing the data inside of Canary. I will mention that often questions are going to come up, and because this is recorded, it may be difficult for you to easily feel like you can get answers to that. We welcome you to email us at any time, info@canarylabs.com. You can stay anonymous if you'd like, or of course, use a business email and we can start a conversation about your needs. But any questions that you might have here on part 1, feel free to email us info@canarylabs.com, or you might consider using our community, helpcenter.canarylabs.com. You can find it from our website. All right, the second video, or the next video in this series, is going to focus on how we contextualize the data, and will feature the calcs and events and the views portion of our Canary System map.